I'm really sorry I can't be with you today, but nevertheless, hopefully we're going to have a lot of fun today learning with me and with the cover teacher. Hopefully you're going to be on your very best behavior like you always are. As always, guys, can you go into the back of your science book and, working in silence, can we answer these questions? Okay, hit pause. Okay, excellent. Right, first question then. Purple pens out, please. We're going to check and we are going to annotate, correct our answers if we need to. Why can't solids flow? Right, we have this picture of a particle model of a solid. We should know how to do this by now. Remember, this is our two-dimensional picture of what's going on in a solid. And I'm really sorry, these are meant to be circles. I'm not making a very good job of this. Never mind. These are all circles, and they are representing the particles in a solid. They are supposed to be all the same size. They're supposed to be not overlapping. However, this could be a lot better. It's difficult right now. However, why can't solids flow? In between these different particles, there are what we call strong bonds of attraction. Okay, those are holding the particles in this three-dimensional shape. Remember, this is the two-dimensional shape. In 3 dimensions, we build up a huge solid over and over again, these particles, but they're vibrating a bit, but they are not moving, at least not moving past each other. So solids cannot flow because of these strong bonds of attraction. Hopefully you got something like that, and I'll show you all the answers at the end. In which states of matter do the particles have the most energy? Right, back to our version of particle models. Again, apologies for these not being very circular. You obviously, hopefully, will take much more time getting this right than I'm doing. However, we have our at least 9 circles representing the particles in solids, in liquids, and then finally we'll do some more in gases. So, solid, liquid, and gas. These are moving, but not much. They are vibrating on a fixed point in a solid. In a liquid, well, these are moving round past each other. Their forces of attraction are less. These, we see, have got more energy. That allows them to move. However, in a gas, these are very far apart, and they are free to move in all directions. And they do. They have lots and lots of energy. So the state of matter with the particles have most energy is the gas. How does increasing the temperature affect diffusion? Well, okay, remember our tea. We made some tea in cold water and we made some tea in hot water. And the hot water tea happened much, much quicker. Yes, it took a week for the cold water tea to be made, but still increasing the temperature increases how quickly diffusion can happen. Again, I'll show you all the answers in a second. What is kinetic theory? Right, this is something that students often struggle with. This word kinetic, it just means moving or movement. That's all it means. It's not a word we normally use in English, but it's a word we can definitely use in science and physics and chemistry. Simply, it states that particles in materials move. They move in different ways, depending on whether it's solid, liquid, or gas, but they move. Again, I'll show you the answers in a second. What is the name of the process of liquids turning to solids? Right, this is something we're going to look at today. We know this word because it's a word we use in everyday language. Liquids, if you put liquid water into a machine in our kitchen, it will turn into solid water, and we'll generally call that ice. And we should put that into our freezer. The process is called, therefore, freezing. Let's just check our answers so we can stop the video in a second and we can get our purple pens and check through. Away you go. Okay, excellent. So hopefully we all got at least 4 out of 5, and hopefully many of you got 5 out of 5. Okay, yes, Simon. Already, I've put up onto Show My Homework your homework for this week. I'm glad to say that the vast majority of you have done your homework on carousel learning, and those who haven't, I'm going to be catching up with you when I return. It's up there. There is a hyperlink in blue, and that will take you to carousel learning for this week's quiz. It's going to be all about particles as before, this time adding a little bit more about state changes, freezing, um, evaporating, all the rest. If you're having problems, must email me. My email address is here at the bottom. Please make a note. There's no point in telling me on Sunday afternoon that you can't do it if I don't know that. If I don't know that on a Friday, I don't know that on a Thursday when I can do something about it. Okay, I'm busy doing other things at the weekend, so please don't leave that. I will try and sort it out if I can. If you leave it too late, I can't. Right, let's get on with our lesson for today then. In the fronts of our books on the next available page, I'm going to give you, or the teacher is going to give you about 3 minutes to write this down so we can pause the video while you do that. Excellent. Okay, so today we're going to look again at heating and cooling curves. So we're going to review what we did in our last lesson, and then we're going to examine melting and boiling points and changes of state. We're going to use lots of keywords, including words we've seen before already, but some new keywords which hopefully we can then use throughout the lesson. Here is the figure that you have in your booklet, and we have our 3 states of matter. There are 3 you need to know about for Key Stage 3 Science, for Year 7 and 8 Science, and these are the 3. We already know, though, they can change state. So if we heat up a pure substance, it will eventually melt. And when it melts, that material becomes a liquid. If we keep on heating that material, this time from a liquid, it will turn into a gas, and this we call boiling. And it also involves evaporation. Going the other way, if we cool a gas down, if we take away some of that energy, if we cool it down, the gas will turn to a liquid. And this is what we call condensing or condensation. And similarly, if we remove the energy from the particles in the liquid and we cool it down, like putting some liquid water into the freezer, it will freeze. And by freezing, we mean it will turn into a solid. It's really important to mention that none of these things are chemical reactions. These are physical changes of state. If it's water here, solid water, it will still be water here, liquid water. And then it will still be water, but in a gas form, steam, or what we call water vapor. And the same the other way around. There is no change in the water particles. What changes is what they are doing, their behavior, and we'll look at that in a bit more detail. Right, you've seen this before. Here is our picture of a thermometer, degrees Celsius. And we've seen this picture before. I'm just going to talk you through it in stages. For a pure substance, we have this idea that it will have a temperature at which it melts. And also it will have a temperature at which it boils. And for any pure substance, any temperature below the melting point on this scale, that pure substance will exist as a solid. Now, we know water, we think of water, it doesn't have to be water, it could be metal, it could be lead, it could be magnesium. If it's pure, then this will be solid if the temperature is below the melting point. If, however, it is between the melting point and the boiling point, then that tells us that this substance will be a liquid. It could be water. Liquid water is something we are familiar with, but it could be any other pure substance. It could be chlorine. It could be oxygen. Now, above the boiling point, it means we've added extra energy. Those liquid particles, those particles within the liquid have now got so much energy they're escaping from the liquid and they're becoming a gas. They're spreading out and they're moving really, really quickly. Very high energy. So we're going to use these ideas today when we review our curve from last week. So last week we created a heating curve by using a hot plate to heat up water. And I'm going to show you what I did to make that a bit clearer as to what's happening. Here were our data, and you should have a copy of this in your book. We set up our table like this. We have the time on the left-hand side, and we add the units, which were minutes. And on the right-hand side, this is a thing that we were measuring. This was what we call our dependent variable. That's something we're going to look at in the future. But for now, we'll just simply say that we were measuring the temperature and we're using the units of degrees Celsius. So we basically had ice, solid water. At 0 time, at the beginning, it was 0 degrees Celsius. But then, in time, we measured every 2 minutes. The water got hotter and hotter and hotter until we got to a point when, after 20 minutes, there was no change. It got to 100 degrees Celsius, but it did not change. So what does that look like in a graph? Now, a table of data is great. It gives us lots of clues, but even better is this. So these are our data. Let's just go through what it means. So along the bottom, we have the time going up in twos, so 2 minutes, 4 minutes, etc. But at the side, we had a thing that we measured, the temperature. You notice the temperature stayed at or about 0 degrees C for a few minutes. I think this surprised some of us. It stayed there for about 4 minutes. And then there was an increase, and look how steady that increase is. It's going up every 2 minutes, about the same amount. But then, and again, some of us were surprised with this. Some of us were thinking it was going to go off forever and ever, but it doesn't. Liquid water cannot go above 100 degrees Celsius. So this shows that above 100 degrees Celsius, something else is going to be happening. Here, liquid water, the temperature of liquid water cannot go above 100 degrees Celsius. So this is our heating curve for pure water. And if we turn to the page in our booklets, after the work we did last week, you will see something which looks like the next picture. So if we turn to that page, you should see this. Okay, let's read what it says at the top, nice and slowly. Go through it and we can underline keywords and we'll think about what this means. What happens at the melting and boiling point? So we should know what we mean by melting. This is when a solid becomes a liquid. What happens at the boiling point? Well, boiling, this is where the liquid becomes a gas. Wow. When energy is added to a substance, its temperature increases. We heated this up with our hot plate. The temperature increases. However, when it gets to its melting or boiling point, its temperature does not increase. This is because all of the energy being added is then used to help break these forces of attraction between the particles. So as we saw at the beginning of our graph, it didn't change much. And at the end of our graph, it stayed at 100 degrees C. And look, so if you heat up some liquid water, when it hits 100 degrees, it will stay at that temperature for a little while, as it then begins to turn into steam. If you heat up some liquid water when it hits 100 degrees C, this is the boiling point, it will stay at that temperature. The energy from the heat source is then causing the particles to break apart from each other. The particles aren't breaking apart. The particles are breaking apart from each other. So if we had them close together, by adding energy, we then force them to break apart from each other. Now it is a bit more complicated than that, and you'll find a lot more out about this in year 9 and 10. However, for the minute, that's all we need to know. So what's going on here? Well, this middle bit between here and here looks very much like our graph. But what's going on at the other ends? We've got to imagine in our head a scale of temperature. Now, we always think about water. We don't have to. Okay? What we're going to be doing is adding heat. We're going to be heating up this material. It could be water, it could be anything else, any pure substance. Let's look at this scale. This down here is a low temperature. And somewhere up here, there'll be a high temperature. This is the way our scale works. So right down here, this material is going to be a solid. It could be solid water, it could be solid lead, it could be solid carbon dioxide. Doesn't matter. What are we doing, however, between A and B? Between A and B, we're adding heat. We're adding heat energy. Now it's still solid, but those particles are now getting a little bit more energy. They're moving, but now they're moving a little bit more, vibrating a little bit more until they get to this point. And this is the melting point. For any pure substance, this will have a fixed value. And at this point, we saw that our temperature didn't increase. It stayed at 0 degrees C. So here to here, the ice is melting. The lead is melting, the carbon dioxide is melting. And it's happening here over this period. Now, the more we add, the more it's going to melt, and those bonds are going to start to be broken. However, it will not change temperature. When it's all melted, then if we add more heat for this period between C and D, the substance is going to be a liquid. And it will remain a liquid as we keep adding more heat energy until we get to D. And point D, well, this will be for any substance, any pure substance, the boiling point. Doesn't matter what it is. It could be iron, it could be magnesium, it could be oxygen, it could be anything. If it's a pure substance, it will have a melting and a boiling point. So now this does not change for a while. At this point, the substance is boiling. The temperature isn't changing, but those particles are getting extra energy to eventually allow them to form a gas. The particles themselves will not change, they'll just get more energy. And eventually, they will all evaporate and they will all then form a gas. Now the gas can heat up, and the gas heating up can continue way up here. But now we're adding more and more energy, and the gas can get as hot as it likes. Okay, getting hotter and hotter means those particles are going to move faster and faster, moving further and further apart, and that can continue. Okay, so here is our heating curve for any material. Bottom end, we have a low temperature where the material is solid, and then it melts, and it melts at the melting point. After that, after it's all melted, it's a liquid, and it's a liquid until we reach the temperature of the boiling point. And at that point, it will boil. However, the temperature will not change. But then, above that temperature of the boiling point, it will become a gas, and that will continue to get warmer and warmer as we're adding more and more energy. So, excellent. We're now going to answer the questions. For each of the answers, you can pick just letters, 1 or 2 letters. The first one has been done for you, so we'll just look through the first one, and then you can have a go by yourselves. So, question 1. Between which letters is melting taking place? It says answers B and C. Let's have a look why. We've got letters A, B, C, D, E, F. We've got 2 temperatures noted. The lower one is a melting point, the higher one is a melting point. So where is it melting? Well, I'm looking for a flat line where the temperature isn't changing, but where it's changing from a solid to a liquid. That's what melting means. So we can see it between points B, point C, that is happening. So that's a good answer. So I'm going to leave you now for 5 minutes. Try to do this independently, writing single letters. If you want to write an explanation, that's even better, and that's the kind of work we could be doing as we prepare for year 8. But at the moment, a single letter with an explanation to assist. Stop the video and we'll pick it up again in 5 minutes. Okay, at which letter? So it's only one letter here, we don't need 2 letters. At which letter does boiling start to take place? Boiling starts to happen here, time or the part D. So the answer there was part D. Which letter is a substance at its hottest? Temperature low, temperature high. We go all the way up here. Hottest, at least on this graph, is F. Good. Well, which letter is its coldest? Well, cold means a low temperature, so way down here. There we go. Which letter, between which letters, so we've got 2 letters here now, is a substance a liquid and heating up? So we've got to look for when it's a liquid and heating up or getting warmer. Liquid, getting warmer. So between which 2 letters? Well, between C and D. Between C and D. Between which letters is a substance a solid and heating up? Between which letters is a substance a solid and heating up? So we've got the key word there, solid. Let's look. Right, at a very low temperature, this substance will be a solid. So here we go, and it's heating up. You can tell that the temperature is rising. A and B. And now, between which letters is a substance a gas and heating up? Gas and heating up. Right, up here we have our gas and it's getting warmer. We're adding energy. The temperature is increasing. So here's our temperature scale increasing. So between E and F. Fantastic. Between E and F. At which letter do strong forces of attraction start to get broken? Now we need to do some science. What does that mean? At which letter do strong forces of attraction start to get broken? We need to know things about materials. The strongest forces of attraction happen in solids. So how do we know when strong forces of attraction start to get broken? Well, that must mean that the material is beginning to become a liquid. That's why materials change from a solid to a liquid. So we're going to be looking for a point when a solid is starting to become a liquid. Here's our solid. Now, using our keyword, turning a solid into a liquid means melting. So there's that keyword there, melting. So at what point is the solid beginning to melt? Well, right here at position B. And that's our answer. So again, that last one was more difficult. 1, 2, 3, 4, 5, 6, 7 questions. Correct any mistakes and write down how many out of 7 we got right. Excellent. Okay, so Today we have been looking at cooling curves, reminding ourselves what they mean, reminding ourselves how we made our cooling curve and heating curve last time, so we can then examine what it means to melt, what it means to boil, and how we can then investigate those changes of state. Thank you very much, Year 7, and hopefully I will see you very, very soon. Have a good day.